The morning of November 10th, 1942, somewhere over the East China Sea, a Japanese test pilot whose name has been lost to history sits in the cockpit of an enemy aircraft. His hands rest on the control yoke of a North American B-25 Mitchell bomber, one of the raiders from Jimmy Doolittle's attack on Tokyo 6 months earlier. The aircraft had been recovered, painstakingly reassembled, and made airworthy again. Now, for the first time, a Japanese aviator is about to discover what the Americans have built. He advances the throttles. The Wright R-2600 engines roar to life with a sound unlike anything in the Imperial Japanese inventory, not the high-pitched scream of a Nakajima radial, but a deep, sustained thunder. 1,400 horsepower per engine, 2,800 total. The instrument panel vibrates. The whole airframe shakes with barely contained power. He releases the brakes, and Mitchell surges forward, heavier than any bomber he has ever flown, yet accelerating with an authority that feels almost violent. The tail comes up, the runway blurs beneath him, and then he is airborne, climbing out over Tachikawa airfield with an enemy's machine beneath his fingertips, about to learn a truth that will haunt Japanese military aviation for the remainder of the war. This is not a story about the Doolittle raid itself. That narrative has been told and retold: the audacious carrier launch, the symbolic strike on Tokyo, the desperate escapes into China. This is about what came after, about the engineers and pilots who inherited the wreckage, about what they found when they put those broken American bombers back together and flew them, about the reports they wrote, clinical, precise, devastating, that travelled up through Imperial General Headquarters. Reports that said, in careful technical language, that the Americans had discovered something Japan had not. That forward-firing offensive power integrated into the bomber itself, changing the nature of air combat. And that Japan, for all its early victories, for all the Zero's dominance, for all the audacity of Pearl Harbor and the sweep through Southeast Asia, was building its aircraft on principles that would not survive the war they had started. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand what those Japanese engineers discovered when they flew the captured B-25, you must first understand what the Mitchell represented in 1942 and why its design philosophy was so fundamentally different from everything Japan had built. The B-25 Mitchell was not, by any objective measure, a revolutionary aircraft. It did not break speed records. It did not fly higher or farther than its contemporaries. Its twin Wright R-2600 engines were powerful but not unprecedented. Its airframe was conventional mid-wing monoplane, twin vertical stabilizers, tricycle landing gear. When North American Aviation received the contract to design a medium bomber in March of 1939, they were not asked to invent the future. They were asked to build something practical. But practical, in the American industrial context, meant something very different than it did in Japan. Mitchell's design philosophy was predicated on assumptions that could only emerge from a nation with vast industrial capacity and resources that seemed, if not infinite, then at least abundant enough to permit a certain philosophical luxury. The B-25 was overbuilt. Its airframe used aluminum extrusions and panels thicker than strictly necessary for flight. Its structural members incorporated safety factors that Japanese engineers, trained to eliminate every unnecessary gram, would have considered wasteful. The hydraulic systems were redundant. The electrical wiring was shielded and duplicated. The engines, those massive R-2600 seconds, were designed to tolerate damage and continue running even with cylinders shot out. This was not elegant. This was an American manufacturing philosophy translated into aluminum and steel. If you build it strong enough, it will bring the crew home. Japanese bomber design in 1942 operated from entirely different premises. The Mitsubishi G4M, called the Betty by the Allies, could fly over 2,000 miles, an extraordinary range that allowed Japanese naval aviation to project power across the vast Pacific. But that range came at a cost, measured in millimeters of aluminum, in the absence of armor plating, in fuel tanks that were not self-sealing. The Betty was fast and deadly, but it was also in the brutal arithmetic of air combat flammable. American pilots called it the one-shot lighter because a single burst of .50 caliber fire could ignite it. This was not poor engineering. This was a strategic calculation. Japan's war plan depended on striking first, striking hard, and establishing a defensive perimeter before American industrial might could be brought to bear. Japanese bombers were designed to achieve maximum range and speed with minimum weight. They would hit targets the enemy could not reach, and by the time American forces arrived in strength, Japan would be too deeply entrenched to dislodge. It was a reasonable theory, and for the first 6 months of the war, it worked. But the B-25 represented a different theory of air warfare entirely, one that assumed prolonged conflict, attrition, and the necessity of bringing damaged aircraft home to fight again. And buried in its design was something else, something more ominous, the idea that the bomber could be an offensive weapon not just in the bombs it dropped, but in the guns it fired. In 1941, when the B-25 entered service, most bombers, American, Japanese, German, British, operated on similar principles of defensive armament. They carried machine guns in positions designed to protect against fighter attack, tail guns, dorsal turrets, ventral positions, waist guns. The bomber defended itself while bombardiers aimed and released ordnance. The pilot flew the aircraft. The gunners fought off interceptors. These were separate functions. But in the Pacific theater, American units began experimenting with modifications that violated this separation. B-25 seconds, operating out of Australia and New Guinea against Japanese shipping, started mounting additional machine guns in the nose, aimed forward, fired by the pilot. The aircraft commander traditionally focused solely on navigation and formation. Flying became a gunfighter. By mid-1942, field modifications were producing B-25 seconds with 4, then 6, then 8 forward-firing .50 caliber machine guns. The logic was straightforward. When attacking ships or ground targets at low altitude, the bomber spent crucial seconds in its final approach exposed to anti-aircraft fire. What if, instead of simply enduring that fire, the bomber could suppress it? What if the pilot could aim the entire aircraft at the target and open fire while simultaneously positioning for bomb release? The .50 caliber Browning machine gun, the standard American heavy machine gun, fired a half-inch diameter bullet at a muzzle velocity of 2,900 feet per second. Its effective range exceeded 1,000 yards. A single .50 caliber gun could fire 750 rounds per minute. 8 of them, firing simultaneously, could put 100 rounds per second into a target area. That volume of fire could shred wooden structures, penetrate thin armor, kill exposed personnel, and critically make anti-aircraft gun crews abandon their positions or die. This was the B-25's revelation. Forward-firing power transformed the bomber from a passive platform that delivered ordnance while hoping to survive, into an active predator that could fight its way to the target. Japan did not yet understand this. In November of 1942, when that test pilot climbed into the captured Mitchell at Tachikawa, Japanese bomber doctrine still emphasized range, speed, and defensive gunnery. The idea that a bomber might attack forward, that the pilot might aim and fire like a fighter, was foreign to their operational thinking. They were about to receive an education. April 18, 1942. 16 hours after the Doolittle raid. Captain Edward York's B-25, aircraft number 40, is running out of fuel somewhere over the Sea of Japan. York faces a decision with no good outcomes. His original orders were to bomb Tokyo and proceed to Chinese airfields controlled by nationalist forces. But weather, navigation errors, and fuel consumption higher than calculated have put him too far north. China is out of reach. Ditching in the ocean means probable death for his entire crew. There is one alternative, forbidden by the mission plan, but suddenly the only viable option: divert to Soviet territory. The Soviet Union, in April of 1942, occupied a strange position in the global war. Locked in a death struggle with Nazi Germany, desperate for American aid, Stalin's government has no desire to provoke Japan. The Soviets and Japanese signed a neutrality pact in April of 1941 that both sides have scrupulously honored. Soviet ports in the Far East remain open. The Trans-Siberian Railway continues to carry supplies. Japan, bleeding resources in China and planning expansion into Southeast Asia, needs that neutrality. The Soviets, with German armies driving toward the Caucasus, cannot afford a two-front war. York knows this. He knows that landing in Soviet territory will mean internment for his crew, but it also means survival. He turns north. The B-25 lands at a Soviet airfield near Vladivostok with its fuel tanks nearly dry. Soviet officials, caught between diplomatic necessity and personal sympathy, intern the crew. York and his men will spend next year in various Soviet facilities, not prisoners, exactly, but not free. They will eventually escape across the border into Iran in May of 1943, a story of its own complexity. But the B-25 itself does not escape. What happened to York's aircraft in Soviet custody remains one of those murky episodes that World War II produced with remarkable frequency. Official Soviet records are incomplete or still classified. American intelligence summaries from the period contain contradictions. Some sources suggest the aircraft was sold to Japan through intermediaries. Others hint at a more complex exchange involving technology, resources, or simply Soviet unwillingness to house evidence of American military operations on their soil. What is documented is this. By August of 1942, a mostly intact B-25, almost certainly York's aircraft, was in Japanese hands at a military facility in Manchuria. The Soviets had, through means not fully recorded, transferred an American bomber to Japan, while maintaining official neutrality with both nations. This was not the only B-25 the Japanese acquired. Lieutenant Ted Lawson's bomber, aircraft number 7, had crashed on the Chinese coast after attacking Tokyo. Lawson's account, published after the war as 30 Seconds Over Tokyo, describes the belly landing in darkness, the desperate escape through surf, Lawson's severe injuries. The crew escaped, but the aircraft remained, badly damaged but largely intact, in Japanese-occupied territory. Lieutenant Bill Farrow's aircraft came down near Nanchang. Farrow and his crew were captured. They would be subjected to show trials, torture, and execution. 3 of them beheaded in October of 1942, a war crime for which Japanese officers would later hang. But before those executions, Japanese forces recovered Farrow's bomber. Lieutenant Don Smith's B-25 also crashed in occupied China. Smith and most of his crew evaded capture with the help of Chinese civilians. The bomber stayed behind. By summer of 1942, Japanese technical intelligence services had access to multiple B-25 airframes in various states of damage. The decision was made at high levels: recover everything, understand everything, reconstruct a complete aircraft if possible. The recovery operation was extensive and methodical. Japanese engineers arrived at crash sites with detailed instructions. Chinese laborers, working under Japanese supervision, disassembled the wrecks panel by panel. Each piece was catalogued, numbered, photographed. Crates were constructed on-site to protect sensitive components during transport. Railway cars carried the pieces to ports. Cargo vessels transported them to Japan. The most complete airframe York's bomber from the Soviet transfer was prioritized for restoration. Wings were transported separately from the fuselage to prevent structural damage. The R-2600 engines, each weighing over 2,200 pounds, were carefully packaged with particular attention to the turbochargers and reduction gears. Instruments, radios, gun turrets, even the oxygen systems, everything was preserved. At Tachikawa Army Airfield near Tokyo, a special technical team assembled in July of 1942. Their mission was not merely to study the B-25, but to restore one to flight status. The team included graduates of the Imperial Japanese Army Air Academy's Technical School, engineers from Nakajima and Mitsubishi, with experience in American manufacturing methods, specialists in metallurgy and avionics. For 3 months they worked. The challenge was not simply mechanical restoration but philosophical translation. The B-25 had been built using American industrial processes, American standards, American assumptions about materials and tolerances. Japanese engineers, trained in a system that prized precision, hand-fitting and minimal material use, had to reverse engineer not just the aircraft but the thinking behind it. They began with documentation. The B-25 carried technical manuals, maintenance logs, manufacturing specification plates. These were photographed and translated. They revealed American part numbering systems, quality control processes, approved substitutions, and field modifications. The Americans documented everything. Japanese technical practice relied more heavily on skilled craftsmen who understood processes intuitively. The American approach was to write down every detail so that any mechanic, anywhere, could maintain the aircraft. This was a clue to something larger. As the team disassembled and studied components, patterns emerged. The aluminum panels used in the B-25's skin were thicker than equivalent Japanese components, not by dramatic margins, but consistently throughout the airframe. Structural members incorporated larger safety factors. Bolts and rivets were standardized in sizes that allowed for easier replacement but used more material than strictly necessary. One engineer's report, preserved in captured documents now held in American archives, noted, "American construction philosophy appears to prioritize ease of manufacture and field repair over weight optimization. Components are designed for replacement rather than repair. This suggests production capacity sufficient to treat entire assemblies as expendable." They were reading the B-25 as an artifact of American industrial civilization, and what they read was sobering. The hydraulic systems incorporated redundancies that Japanese designers would have eliminated. If one hydraulic line failed, backup systems could operate critical flight controls. The electrical system was similarly duplicated, with multiple generators and battery systems. The Americans were building an aircraft that could absorb significant battle damage and continue functioning. The engines were revelatory. The Wright R-2600 Cyclone was a 14-cylinder radial producing 1,400 horsepower. Japanese engines of similar displacement produced less power, but the true difference was in durability. The R-2600 incorporated robust crankshafts, heavy-duty connecting rods, and superchargers designed for sustained high-power operation. It could run with damaged cylinders. It could tolerate overheating that would destroy Japanese engines. It was not a precision instrument. It was an industrial machine designed to keep running under abuse. By October of 1942, the team had restored the B-25 to flight status. They had hand-fabricated replacement parts for damaged components. They had filled its fuel tanks with Japanese aviation gasoline, loaded American .50 caliber ammunition taken from other wrecks, and certified the aircraft airworthy according to Japanese test procedures. It was time to fly it. The test pilot assigned to fly the captured B-25 was an experienced officer, almost certainly a graduate of the Army Air Academy at Kumagaya, with combat time over China or the opening campaigns of the Pacific War. His name does not appear in surviving documentation. Japanese military records from this period often omitted such details from technical reports, focusing on data rather than personnel. But his qualifications would have been substantial. You do not assign an inexperienced aviator to evaluate a captured enemy aircraft that represents months of recovery effort and significant intelligence value. He would have conducted the standard pre-flight inspection, walking around the aircraft, checking control surface movement, examining the landing gear, verifying fuel quantities, but everything would have felt different. The B-25 sat higher off the ground than Japanese bombers. Its tricycle landing gear, nose wheel forward, main gear under the wings was not standard Japanese practice. Most Japanese aircraft used conventional tail-dragger configurations. The Mitchell's stance gave it a level attitude on the ground, the fuselage parallel to the earth, rather than tail down. This was an American innovation, providing better pilot visibility during taxi and takeoff, reducing the risk of ground loops, and simplifying landing approaches. Even stationary, the B-25 communicated a different philosophy. The cockpit entry required climbing through a hatch in the nose and moving aft to the flight deck. Once seated, the pilot faced an instrument panel that was comprehensive rather than minimal. American aircraft in 1942 already featured standardized instrument layouts, the basic 6 flight instruments in a consistent T pattern, engine gauges grouped logically, and system controls clearly labeled. Japanese cockpits of the period were more variable, with instruments and controls positioned according to individual designers' preferences. The Americans had systematized even this. The control yoke was substantial, mechanically linked directly to flight surfaces through cables and pulleys. Control forces would be heavier than in a Japanese bomber. The B-25 did not have hydraulically boosted controls, but the response would be positive and predictable. The throttle quadrant on the cockpit center console controlled both engines, propeller pitch, and mixture settings. Everything was accessible. Everything was logical. The test pilot started the engines using the procedures documented in the translated manuals. Electric starters spun the R-2000, 600 seconds to life. The sound was distinctive, a deeper, more mechanical rumble than Japanese radials produced. 1,400 horsepower per engine was not unprecedented in Japanese aviation, but the character of that power felt different. The right engines settled into a steady idle that shook the entire airframe. They sounded barely civilized, like industrial equipment rather than precision mechanisms. Taxi out to the runway at Tachikawa, The nose wheel steering simplified ground handling. Visibility over the nose was excellent. The Mitchell felt heavy during taxi, its empty. Weight exceeded 20,000 pounds, several thousand pounds heavier than a comparable Japanese bomber like the Ki-49 Helen. But the engines had power in reserve. Even at idle, they radiated authority. Takeoff checklist, flaps set, trim adjusted, engines run up to check magnetos and propeller pitch control. The test pilot advanced the throttles smoothly, keeping the aircraft straight with rudder inputs as asymmetric thrust tried to pull the nose sideways. Mitchell accelerated down the runway, gaining speed with what must have felt like surprising authority. The tail came up naturally as airspeed increased. At roughly 90 miles per hour, the aircraft simply flew off the ground with no particular effort required. Gear up, flaps up, climb power set. The B-25 climbed away from Tachikawa, and for the first time, a Japanese pilot experienced what American bomber crews had been flying since 1941. The first impression documented in subsequent reports was speed. At cruise, power and altitude, the B-25 was faster than expected. Maximum speed approached 300 miles per hour at medium altitude, not exceptional by fighter standards, but remarkable for a bomber carrying a substantial bomb load. More significantly, the Mitchell maintained high cruise speeds efficiently. This was not a sprinter that exhausted itself quickly. This was sustained performance. The test pilot conducted standard evaluation maneuvers, turns at various bank angles and airspeeds, climbs at different power settings, descents with throttles reduced, single-engine operations with one engine feathered. Mitchell responded predictably throughout. Control forces were heavier than Japanese bombers, but the aircraft was stable. It did not exhibit dangerous characteristics. You could feel its mass, its solidity, but it was not unwieldy. Then came the critical evaluation, high-speed dive and recovery. This was the test that revealed structural integrity, the maneuver that Japanese bombers often failed catastrophically. The Betty, for all its range and speed, could not dive steeply at high speed without risking structural failure. Japanese bomber doctrine emphasized level bombing from altitude, specifically because their aircraft could not safely conduct dive bombing attacks. The test pilot pushed the B-25's nose down and let it accelerate. Airspeed increased rapidly. The control surfaces stiffened as dynamic pressure built up, but they remained responsive. The aircraft did not flutter or vibrate. At speeds approaching the never-exceed velocity marked on the airspeed indicator, the Mitchell felt solid. Then came the pull-out, a smooth, sustained pitch-up that loaded the airframe with several times the force of gravity. No structural concerns, no alarming noises, no flexing or distortion. The report filed after this flight noted, in careful technical language, structural rigidity exceeds that of current Imperial Army bomber types. Control response remains positive during high-speed maneuvers. No structural limitations observed within the tested flight envelope. Translation: this aircraft is built stronger than ours, but the most significant discovery came during simulated attack runs. The test pilot, following evaluation protocols, conducted low-altitude approaches, simulating attacks on surface targets, ships, ground installations, the scenarios for which medium bombers were designed. He descended to low altitude over Tokyo Bay, aligned the B-25 with an imaginary target, and advanced the throttles for an attack run, and that is when he experienced the forward-firing armament. The captured B-25 was not one of the heavily modified strafer variants that would appear later in the war. It retained its original configuration, a bombardier's station in the greenhouse nose, defensive gun positions, and whatever forward-firing guns had been fitted before the Doolittle raid. But even that standard armament included forward-firing capability. The bombardier's position mounted at least one flexible 30-caliber machine gun that could fire forward. Some of Doolittle's raiders had added fixed 50-caliber guns in the nose before the mission. Even this minimal forward armament represented something Japanese bombers lacked. The test pilot aimed the entire aircraft at the target point and opened fire. The experience was fundamentally different from conventional bomber operations. Instead of merely flying the aircraft to a release point while bombardiers and gunners performed their separate functions, the pilot became an active participant in the attack. The B-25's nose, with its extensive glazing and forward-firing guns, became a fighter's office. You could see the target clearly, you could aim, you could fire, and you were doing all of this while simultaneously positioning for bomb release. The psychological effect was profound. In a Japanese bomber, the pilot was in a sense a chauffeur. You flew the aircraft to the target area. The bombardier aimed and released ordnance. The gunners defended against interceptors. These were separate, specialized functions. But in the B-25, equipped with forward-firing guns, those functions collapsed into unified action. The pilot became a hunter, not merely transport. The tactical implications were immediate and obvious. Forward-firing armament allowed the bomber to suppress defensive fire during the final approach. Anti-aircraft gun crews faced not just an approaching aircraft dropping bombs, but an aircraft actively shooting at them. The psychological pressure on defenders was multiplied. You could not simply aim and fire at an approaching bomber. You had to do so while that bomber was firing back, directly at your position. More fundamentally, forward-firing power transformed the bomber's relationship with its targets. Against ships, particularly the kind of lightly armed merchant vessels and patrol craft that dominated Pacific sea lanes, a B-25 with nose, guns became a devastating weapon. It could approach at low altitude, suppress deck guns with machine gun fire, release bombs or torpedoes, and strafe the target during the entire attack run. The ship's crew had to simultaneously deal with incoming fire, maneuver to avoid bombs, and attempt to shoot down the attacker. The test pilot's report, filed with the Army Air Technical Research Institute, stated, "Forward-firing armament provides significant offensive capability during the attack phase. Pilots can engage defensive positions while maintaining an attack approach. Effect on target morale assessed as substantial. Integration of offensive and defensive fire represents doctrinal advancement not present in current Imperial Army types." This was not sensationalism. This was a professional test pilot, trained in objective evaluation, stating in measured language that the Americans had discovered something Japan had missed. Additional test flights followed through late 1942 and into 1943. Other pilots flew the captured Mitchell. Engineers studied its systems in greater detail. The aircraft was used for training Japanese pilots in American aircraft recognition and tactics. Each evaluation produced additional reports, additional data, additional confirmation of the initial findings. The B-25 was faster than comparable Japanese bombers. It was structurally stronger. It had a longer range than expected, despite being heavier. Its engines were more durable. Its systems were more redundant. And critically, almost damningly, it integrated offensive and defensive capabilities in ways Japanese bomber doctrine had not contemplated. In December of 1942, a comprehensive assessment was submitted to Imperial General Headquarters. The document, which survived the war in captured archives, runs to over 30 pages of technical analysis, performance charts, and tactical evaluation. Its conclusion, buried in formal military language, was stark. The B-25 Mitchell represents a design philosophy predicated on sustained operations, structural durability, and pilot-directed offensive engagement. Current Imperial bomber types prioritize range and speed through weight minimization. The American approach appears optimized for attrition warfare and battlefield persistence. Further analysis recommended regarding strategic implications. The engineers and pilots who flew the captured B-25 understood what they were seeing. They recognized it as evidence of a different approach to aerial warfare. They documented it carefully. They reported it through proper channels. And then they waited to see if anyone would act on what they had learned. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The challenge facing Japanese military aviation in 1943 was not merely technical, it was philosophical and industrial. The B-25's design philosophy could not be replicated simply by copying its features. Those features emerged from assumptions about resources, production capacity, and strategic objectives that Japan did not share and could not easily adopt. Consider the basic premise. The B-25 was built heavy because America could afford heavy. Its structural over-engineering required more aluminum, more steel, more manufacturing hours per aircraft. But American industry in 1943 was producing aluminum at a rate that exceeded Japan's total production by factors of 10 or more. The United States mined bauxite domestically and imported more from South America. Aluminum smelting plants, powered by hydroelectric dams in the Pacific Northwest and Tennessee Valley, produced metal in quantities that seemed almost unlimited. Japan, by contrast, imported nearly all its bauxite from the Dutch East Indies and Malaya territories, only recently captured, with mining and shipping infrastructure vulnerable to interdiction. Japanese aluminum production in 1943 totaled roughly 300,000 tons annually. American production that same year exceeded 2 million tons. Every pound of aluminum used in a Japanese aircraft represented a strategic choice about resource allocation. Building heavier, stronger aircraft meant building fewer aircraft. The mathematics were unforgiving. The same calculation applied to engines. The Wright R2600 was built to tolerances and specifications that assumed abundant resources. Its crankshaft was forged from high-grade steel alloys. Its cylinders used superior metallurgy. It could tolerate damage and abuse because it was overbuilt and because replacement engines were available. Japanese engine production operated under different constraints. Metals were more precious. Manufacturing capacity was limited. Engines had to be lighter, had to use less strategic materials, had to be maintained and repaired rather than replaced. This was not a failure of Japanese engineering. Japanese engineers were producing remarkable work under severe constraints. The Nakajima Homare 18-cylinder radial engine, introduced in 1943, produced over 1,800 horsepower from an engine that weighed less than the Wright R2600 and used less strategic materials. It was a masterpiece of lightweight engineering. It was also temperamental, difficult to maintain, and prone to failure under the kind of abuse that American engines routinely survived. The choice was not between good engineering and bad engineering. It was between different engineering philosophies constrained by different resource realities. But the forward-firing armament issue was different. That was not primarily about resources, it was about doctrine. And doctrine could, theoretically, change faster than industrial capacity. Japanese bomber doctrine in 1943 remained committed to the principles that had shaped the Betty, the Helen, the Sally, range, speed, level bombing from medium altitude, defensive gunnery. These principles had worked in China, had worked during the opening phases of the Pacific War, and changing them required acknowledging that the strategic situation had fundamentally shifted. The problem was that by 1943, the strategic situation had indeed fundamentally shifted, and denying that fact would not change it. American B-25 seconds in the Southwest Pacific, under the command of General George Kenney, were being radically modified for low-altitude attack missions. Field modifications initially, then factory conversions. The B-25G variant, introduced in mid-1943, mounted a 75mm M4 cannon in the nose, the same gun used on Sherman tanks. This was not a defensive weapon. This was a bomber configured as a gunship. The B-25H, which entered service in 1944, pushed the concept further. The 75mm cannon, 8 forward-firing, 50-caliber machine guns in the nose, 4 more 50 calibers in blisters on the fuselage sides, 2 more in the dorsal turret that could be aimed forward, and 2 in the tail for rear defense, 14 machine guns and a cannon. Some variants carried even more. These aircraft were not designed to drop bombs from altitude and hope defensive gunners would protect them. They were designed to hunt, to come in at masthead height over the ocean, suppress defensive fire with overwhelming forward firepower, and destroy targets through a combination of gunfire, skip bombing, and rocket attacks. The tactic, refined through 1943 and perfected in 1944, was devastatingly effective. A flight of modified B-25 seconds approaching a Japanese convoy would descend to extremely low altitude, 50 feet or less above the water, where they were difficult to detect and engage. They would approach at high speed, opening fire with forward guns at ranges exceeding 1,000 yards. The volume of fire was psychologically crushing. Deck crews abandoned their weapons. Officers could not effectively command. And then came the bombs, skipped across the water like stones, impacting at or below the waterline where they did maximum damage. The Battle of the Bismarck Sea in March of 1943 demonstrated the tactic's potential. A Japanese convoy carrying troops and supplies to New Guinea was caught by American and Australian aircraft, including heavily modified B-25 seconds. The conventional historical narrative emphasizes the complete destruction of the convoy. 8 transports and 4 destroyers sunk, thousands of Japanese soldiers killed. But the reports from Japanese survivors reveal something more psychologically significant: the sense of helplessness. One Japanese naval officer, interviewed after the war, described the attack. "The American bombers came in so low we could see the pilots. They were firing at us before we could bring our guns to bear. When we did return fire, they did not turn away as bombers should. They came directly at us, firing continuously. Our men were killed with their guns. The ship's bridge was struck repeatedly. We could not function. And then the bombs came." This was the forward-firing philosophy made manifest. The bomber was a predator. Japanese engineers and tacticians studying these developments understood the implications. Several proposals emerged in 1943 and 1944 to modify Japanese bombers for similar roles. The Mitsubishi Ki-67 Hiryu, the Peggy in Allied designation, was designed from the beginning with better armor protection and provision for offensive armament. Some Ki-67 seconds were modified with forward-firing cannon for anti-shipping strikes. The Yokosuka P-1Y Ginga, the Francis, incorporated heavier forward armament and better structural integrity than earlier Japanese bombers. These were steps in the right direction. They represented an acknowledgement that a bomber doctrine needed to evolve. But they came too late, and in insufficient numbers. The Key 67 did not enter service until late 1944. The P-1Y was plagued by engine problems. And by 1944, Japan was no longer fighting the kind of war where incremental improvements to bomber design mattered. By 1944, Japan was losing the air war comprehensively. Pilot training had collapsed. Fuel shortages grounded aircraft. American submarines were sinking Japanese shipping faster than it could be replaced, cutting off the resources needed to produce aircraft at all. The strategic situation had deteriorated to the point where questions about bomber doctrine were academic. The captured B-25 at Tachikawa continued flying through 1943 and into 1944. It was used primarily for training, teaching Japanese pilots to recognize American aircraft silhouettes, to understand American tactics, and to anticipate what they would face in combat. The irony was profound. Japanese aviators studied the B-25 to learn how to fight it, but the lessons it taught about integrated offensive power, about structural durability, about the American approach to air warfare, could not be applied within Japan's shrinking industrial and strategic capacity. The captured B-25 at Tachikawa met its end on November 24, 1944, during a daylight raid by Boeing B-29 superfortresses of the 21st Bomber Command. The target was the Nakajima Aircraft Engine Plant at Musashino, just west of Tokyo. Tachikawa Airfield was not the primary target, but it lay close enough to the bomber stream that aircraft experiencing navigation errors or equipment malfunctions sometimes dropped their loads on secondary targets of opportunity. A formation of B-29 seconds, likely from the 73rd Bomb Wing operating from bases in the Mariana Islands, passed over Tachikawa at approximately 28,000 feet. The precision of what happened next is lost to the chaos of aerial bombardment, but the result is documented. The airfield was struck by high-explosive bombs. Hangars were destroyed. Aircraft on the flight line were damaged or obliterated. Among the losses was the Mitchell bomber that Japanese engineers had so carefully restored and studied. The symbolic weight of this destruction is almost too perfect. An American bomber, captured and studied by the enemy, destroyed by a different American bomber, one even larger, even more representative of American industrial capacity. The B-29 was everything the B-25 had been, magnified, heavier, longer-ranged, pressurized for high-altitude operations, defended by remote-controlled gun turrets, and produced in numbers that Japan could not match. By late 1944, the war in the air over Japan was no longer a contest. It was an execution. The Japanese engineers who had flown the B-25 inches 1942 and 1943, who had written those careful reports about forward-firing power and structural integrity and American design philosophy, were watching their predictions come true in the worst possible way. The war they had warned about, a war of attrition, of industrial capacity, of sustained aerial operations, was destroying Japan from the air. But the story of what those engineers discovered extends beyond the immediate tactical lessons about bomber design. The captured B-25 revealed something more fundamental about the nature of the Pacific War, something about the collision between different approaches to industrial warfare, different assumptions about resources and sustainability. When Japanese test pilots flew the Mitchell and felt its power, its durability, its integrated offensive capability, they were experiencing a manifestation of American industrial philosophy. That philosophy assumed abundance. It assumed that resources were available to build aircraft heavier than strictly necessary, to incorporate redundant systems, to prioritize bringing crews home over maximizing range or minimizing weight. These were not merely technical choices, they were cultural and economic expressions of a nation with vast resources and the industrial capacity to exploit them. Japan had made different choices because Japan faced different constraints. The decision to build lighter, longer-ranged aircraft was rational, given Japan's limited resources and strategic objectives. The early war plan required striking first across vast distances, establishing a defensive perimeter, and then defending that perimeter while negotiating a favorable peace. Aircraft designed for that mission did not need to survive prolonged attrition warfare because the strategy assumed attrition warfare would not occur. But the strategy failed. America did not negotiate. The defensive perimeter did not hold, and suddenly Japan was fighting exactly the kind of war its aircraft were not designed for. The B-25, studied so carefully at Tachikawa, embodied the war Japan was actually fighting rather than the war Japan had planned to fight. And the gap between those two realities, between the war as envisioned and the war as experienced, was the gap that ultimately destroyed Japanese aviation. Consider the numbers. In 1942, when Japanese engineers were reassembling captured B-25 seconds and writing reports about American bomber design, the United States produced 47,000 aircraft. Japan produced 8,600. The disparity was notable but not yet overwhelming. Japanese aircraft were qualitatively competitive. The Zero still dominated Pacific skies. Japanese bombers still ranged across vast distances. The war seemed, if not winnable, at least sustainable. By 1943, American production had increased to 85,000 aircraft. Japanese production reached 16,000. The ratio was worsening, but Japan was still producing modern designs in significant too. Numbers. The Ki-61 fighter, the Ki-67 bomber, improved versions of the Zero. These were capable aircraft that could contest American air power when properly employed. But 1944 revealed the true scale of the disaster. American aircraft production peaked at 96,000 aircraft. Japanese production, hampered by resource shortages, strategic bombing, and industrial disruption, managed 28,000. And those 28,000 aircraft faced systematic obstacles the Americans did not: insufficient fuel for proper pilot training, limited availability of high-octane gasoline for engines, shortages of strategic materials for advanced components, interrupted supply lines that prevented finished aircraft from reaching operational units. The mathematics of attrition warfare are brutal and unforgiving. In a prolonged conflict, the side with greater production, better logistics, and more sustainable operations will eventually prevail regardless of individual weapon quality or tactical brilliance. Japan understood this intellectually. The reports filed about the captured B-25 demonstrated that understanding. But understanding a problem and possessing the means to solve it are entirely different things. The engineers who flew the Mitchell had identified the challenge accurately. American bombers represented a philosophy of durable, offensive air power that could sustain losses and continue operating. Japanese bombers represented a philosophy of lightweight, long-range strike capability that assumed brief, decisive campaigns. When the war became prolonged and attritional, the American philosophy was vindicated. But vindication for one side means catastrophe for the other. By 1945, the question was no longer whether Japan could match American bomber capabilities. The question was whether Japan could continue fighting at all. fuel shortages grounded training programs. Pilot quality collapsed as experienced aviators were killed, and inadequately trained replacements took their places. Aircraft production declined as bombing destroyed factories and supply interdiction cut off raw materials. The industrial base that had produced 8,000 aircraft in 1942 managed fewer than 11,000 in 1945, and many of those were kamikaze aircraft, single-use weapons representing the ultimate expression of desperation. The captured B-25 that had taught Japanese engineers about forward-firing power and integrated offensive capability was ash and twisted metal at Tachikawa. The engineers who had studied it were scattered, some drafted into increasingly desperate military service, some working in factories that were themselves being bombed, some already dead in the fire raids that consumed Japanese cities through 1945. And overhead, American bombers continued their work. B-29 seconds flying from the Marianas, B-24 seconds from the Philippines, B-25 seconds, the same type that Japanese pilots had once studied so carefully operating from captured bases in the Ryukyu Islands, striking targets in Kyushu and southern Honshu. The irony that Japanese engineers had flown the B-25 and recognized its capabilities in 1942, 3 years before the war's end, makes the story particularly haunting. They had seen the future, they had documented it, they had warned about it in careful professional language, and there was nothing they could do to prevent it. This is not a story about superior virtue or inherent superiority of one nation over another. It is a story about the collision between strategic plans and strategic reality, about the gap between what you prepare for and what actually happens. Japan prepared for a short war of rapid conquest and negotiated settlement. Japan built aircraft optimized for that war. When that war failed to materialize and was replaced by a prolonged industrial struggle, Japanese aircraft and Japanese strategy could not adapt quickly enough. The B-25 Mitchell that Japanese engineers reassembled and flew represented the other side's preparation. It was built for a different kind of war, a long, grinding, attritional conflict where durability mattered more than elegance, where offensive power mattered more than range, where bringing crews home to fight again mattered more than maximizing individual mission capability. And when the Pacific War became exactly that kind of conflict, the B-25's design philosophy was proven correct. Not because American engineers were smarter or Japanese engineers were foolish, but because American industry could support the B-25's philosophy and Japanese industry could not. The final accounting is stark. The United States produced 9,816 B-25 Mitchell bombers during World War II. They served in every theater. They bombed Germany and Italy. They struck Japanese shipping throughout the Pacific. They supported ground forces in Burma and China. They flew from carriers, from island bases, from captured airfields, and they brought their crews home at rates that Japanese bombers, for all their grace and range, could not match. Japan produced approximately 15,000 bombers of all types during the war. By 1945, most were gone, destroyed in combat, lost to accidents, grounded by fuel shortages, or expended in kamikaze attacks. The industrial capacity to replace them had been bombed into rubble. When Japan surrendered in August of 1945, American occupation forces found Japanese aviation reduced to wreckage and memories. The factories that had produced Zeros and Bettys were burned out shells. The airfields were cratered. The engineers who had once flown a captured B-25 and written reports about American design philosophy were picking through ruins, trying to survive in a devastated nation. Some of those engineers would later work in Japan's post-war aviation industry. They would help design the aircraft that rebuilt Japanese commercial aviation. They would apply the lessons learned during the war, including perhaps some lessons learned from that careful study of the B-25 Mitchell back in 1942. But that is a different story, one of reconstruction rather than destruction. This story ends at Tachikawa Airfield in November of 1944, with B-29's bombs falling through autumn air, with the captured Mitchell burning on the ground, with Japanese engineers watching another piece of evidence turn to smoke. They had known. They had documented what the B-25 represented, what it meant about American capabilities and American philosophy. They had seen the future in that enemy aircraft's design, and knowing had not been enough. In war, understanding your enemy's advantages does not nullify those advantages. Recognition does not equal solution. The engineers who flew the captured B-25 and admitted that forward-firing power was unmatched were not wrong. They were correct. Precisely, professionally, devastatingly correct. But correctness without the capacity to respond is just another form of defeat. The Mitchell bombers that Japanese engineers had studied so carefully continued flying long after the war ended. Some remained in American service through the 1950s. Others were transferred to Allied nations, to the Dutch, to the Indonesians, to various Latin American air forces. A handful were converted to civilian use, and a few, perhaps 20 or so, were preserved and restored to flying condition, where they remain today, appearing at air shows, maintained by dedicated volunteers, their Wright R2600 engines still producing that distinctive thunder. When you see a B-25 Mitchell fly today, when you hear those engines and watch it make a low pass over the flight line, you are seeing an artifact of industrial warfare. You are watching aluminum and steel shaped by a particular moment in history, by particular assumptions about resources and strategy and the nature of aerial combat. And somewhere in Japanese archives, if you knew where to look, you could find the reports written by the engineers who flew this same type of aircraft in 1942. You could read their careful technical language, their professional assessments, their conclusions about forward-firing power and structural integrity and American design philosophy. You could read their warning about the future, and you could see how correct they were, and how completely that correctness failed to change anything. That is the real lesson of the captured B-25. Not that Japanese engineers were incompetent, they were not. Not that they failed to understand what they were seeing, they understood perfectly. The lesson is that in industrial warfare, understanding the enemy's advantages is not the same as possessing the capacity to counter them. Knowledge is not power when power requires resources you do not have. The Japanese engineers who flew the B-25, Mitchell, and admitted its forward-firing power was unmatched, were telling a truth their nation could not act upon. And that truth, documented in careful reports and filed through proper channels, joined all the other truths that wars produce and then consume. Accurate, professional, useless. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The morning of March 3rd, 1943, Squadron Leader Takeo Okumura of the Imperial Japanese Navy's Tainan Air Group circles his A-6M0 fighter at 4,000 feet above the Bismarck Sea, northeast of New Guinea. Below him, a vital convoy 8 transport ships carrying nearly 7,000 soldiers of the 51st Division plows through moderate seas toward Leh. His orders are clear. Protect the convoy at all costs. He's shot down 17 Allied aircraft in the past year. He knows American bombers. He knows their tactics, their weaknesses, their predictable attack patterns. Then he sees them. A formation of B-25 Mitchell medium bombers, approaching from the south at what appears to be impossibly low altitude, perhaps 100 feet above the water. This puzzles him. Medium bombers typically attack from 8 to 10,000 feet. These are coming in at mast height, like torpedo bombers. He radios his flight. 6 Zeros peel off to intercept. Standard doctrine for engaging American medium bombers. Approach from the front quarter where their defensive armament is weakest. Fire a burst into the cockpit and engines. Break away before reaching the tail guns. Okumura has done this dozens of times. His Zero accelerates into a shallow dive, closing the distance. 1,000 meters, 800. The lead B-25 grows larger in his gun sight. It doesn't deviate. It flies straight at him. At 600 meters, he prepares to fire. Then the bomber's nose erupts in light. Not the scattered defensive fire he expects. A solid river of tracers, a visible cone of destruction that seems to fill the entire sky between them. His wingman's Zero, flying 300 meters to his left, disintegrates. Simply comes apart in mid-air, pieces tumbling into the sea. Okumura breaks hard right, yanking his stick so violently he grays out momentarily. When his vision clears, the bomber is gone, already past him, and he's alive only because he reacted on pure instinct. He doesn't know it yet, but he's just encountered the weapon that will rewrite the rules of low-altitude air combat. He's met the B-25 strafer, and nothing in his training prepared him for what he just witnessed. A bomber that attacks like a fighter. A transport aircraft with more forward-firing guns than his entire squadron combined. This is the story of how American innovation transformed a vulnerability into overwhelming firepower, how mechanics in dusty Pacific workshops created a weapon so psychologically devastating that veteran fighter pilots would begin refusing missions rather than face it. This is the story of the aircraft that forgot it was supposed to be prey. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand how this happened, we must go back 14 months to the beginning of 1942, when the B-25 Mitchell was dying in combat, not from design flaws but from doctrinal misapplication. The North American B-25 Mitchell entered service in 1941 as a medium bomber, a designation that defined both its capabilities and its tactical employment. Medium bombers occupied the space between light attack aircraft and heavy strategic bombers. They carried bomb loads between 3,000 and 4,000 pounds, had combat ranges exceeding 1,000 miles, and were designed for horizontal bombing from medium altitudes, typically 8,000 to 12,000 feet. At these altitudes, accuracy suffered, but survival rates improved. Enemy anti-aircraft fire was less effective. Fighter interceptions, while dangerous, gave bomber formations time to organize defensive fire. The B-25's defensive armament reflected this intended role. The B model, which entered combat in early 1942, carried 5 50 caliber M2 Browning machine guns, one in a manually operated turret atop the fuselage, 2 in a dorsal position behind the cockpit, 2 in the tail. For forward defense, a single 30 caliber machine gun mounted in the nose, operated by the bombardier lying prone in the glazed nose compartment. This was considered adequate. Bombers weren't supposed to fight their way through opposition. They were supposed to fly in formation, use altitude as protection, and rely on fighter escorts when available. Then, the war's reality diverged sharply from peacetime planning. In the Pacific theater, distances were vast. Targets were often ships or coastal installations, and weather frequently made high-altitude bombing ineffective. In North Africa, 12th Air Force B-25 seconds found themselves tasked with interdiction missions against enemy supply columns, airfields, and harbour facilities. Both theatres demanded low-altitude attack profiles. The problem with low-altitude attack was simple. It exposed bombers to every weapon on the battlefield. Anti-aircraft artillery could track targets easily. Small arms fire became a threat, and fighter interceptions became far more deadly because bombers had no altitude to trade for speed or maneuverability. The B-25's forward armament became a critical liability. Enemy fighters, particularly German Bf 109 seconds and Japanese Zeros, quickly identified the bomber's vulnerability. Standard interception doctrine evolved. Approach from directly ahead or slightly below, where the bomber could bring only a single 30 caliber gun to bear. Fire a sustained burst into the cockpit and engines, and break away. The bombardier, lying prone and exposed behind clear plexiglass with a lightweight machine gun, faced cannon-armed fighters closing at combined speeds exceeding 500 miles per hour. The engagement lasted seconds. The bombardier rarely survived long enough to return effective fire. Casualty statistics from early 1942 painted a grim picture. In the Southwest Pacific, B-25 squadrons flying anti-shipping missions reported loss rates, approaching 15% per sortie during certain operations. The 91st Bombardment Squadron, operating from Port Moresby, lost 8 aircraft in 3 weeks during April 1942. The 3rd Bombardment Group, flying missions against Japanese positions in the Philippines and New Guinea, saw similar attrition. Aircraft were being replaced. Crews were harder to replace. Each B-25 carried 6 men: pilot, co-pilot, bombardier navigator, radio operator, engineer gunner, and tail gunner. Every aircraft lost meant 6 trained airmen killed, captured, or missing. Pilots knew they were flying into a meat grinder. Captain Edward Larner, commanding officer of the 90th Bombardment Squadron, wrote in his after-action report from May 1942, "Current tactics require medium bombers to attack from altitudes where defensive fire from all sources is most effective. The aircraft's forward armament is inadequate to suppress enemy fighters, making head-on passes. Unless modifications are made to armament or tactics, loss rates will remain prohibitive." The problem was recognized at multiple command levels, but institutional inertia was powerful. The B-25 was designed as a medium-altitude horizontal bomber. Modifying its role meant questioning doctrine developed over years of peacetime planning. It meant admitting that the aircraft, as designed, couldn't perform the missions the war demanded. And institutional military structures, particularly in 1942 when the United States was still mobilizing and learning how to fight a global war, resisted rapid doctrinal change. Into this situation stepped a man who had no patience for institutional inertia and every reason to be angry. Major Paul Irvin Gunn, called Pappy by virtually everyone who knew him, was 42 years old in 1942, ancient by combat pilot standards. He'd served in the Navy during World War I, flying seaplanes on anti-submarine patrol. After the war, he left the military and spent 2 decades in the Philippines, first as a civilian pilot, then as operations manager for Philippine Airlines. He married a Filipino woman, Clara Ormilda. They had 4 children. By December 1941, Gunn had built a comfortable life in Manila, a good job, a family he loved, roots deep in the islands. The Japanese invasion of the Philippines destroyed that life in hours. Gunn managed to evacuate to Australia on one of the last flights out of Manila before the city fell. His wife and children didn't make it out. They were trapped in Manila when the Japanese occupied the city. For months, Gunn had no information about whether they were alive or dead. Eventually, he learned they'd been interned at Santo Tomas internment camp, one of several camps the Japanese established for Allied civilians. They were alive, but they were prisoners, and Gunn could do nothing to help them. He channeled his rage into the war. The Army Air Forces, desperate for Theriot, experienced pilots, commissioned him as a captain and later promoted him to major. Gunn flew combat missions in anything available: B-25 Seconds, B-26 Marauders, even A-20 Havocs. He was fearless to the point of recklessness, pressing attacks long after other pilots would have broken off. But his real contribution wasn't in the cockpit. It was in the workshops and hangars of Townsville and Port Moresby, where he began experimenting with modifications that would fundamentally change air combat in the Southwest Pacific. Gunn's background was crucial. He wasn't just a pilot. He'd spent 20 years keeping civilian aircraft operational on minimal budgets in remote locations. He understood airframes, weight distribution, stress limits, and improvisation. He looked at problems differently than officers trained in the conventional Army Air Forces system. When he saw B-25 Seconds getting slaughtered by frontal attacks, he didn't write reports recommending tactical changes or requesting better fighter escort. He went to the machine shops and started cutting up bombers. The concept was simple, almost obvious in retrospect. If bombers were vulnerable to frontal attack, they would make the front dangerous. Instead of defending against attacking fighters, attack them first. Transform the bomber's greatest weakness into overwhelming offensive firepower. But implementation required solving multiple technical problems. The B-25's nose was a bombardier's station, a glazed compartment designed for visibility, not structural strength. It couldn't support heavy weapons. Mounting guns there would require removing the bombardier's position entirely, which meant losing the ability to perform traditional level bombing. It would change the aircraft's center of gravity. It would add significant weight, and it would require finding space for thousands of rounds of ammunition. Gunn began with available resources. The M2 Browning 50 caliber machine gun was the Army Air Force's standard defensive weapon. It fired a heavy bullet at high velocity, approximately 2,900 feet per second muzzle velocity. The 50 caliber round could penetrate aircraft armor at combat ranges. It could damage engines, and it was already in the supply system, with spare guns available from damaged aircraft and ammunition production already established. Gunn's first modification, completed in early 1943, involved mounting 4 50 caliber guns in the nose of a B-25C. The process was crude but effective. Mechanics removed the glazed bombardier's nose entirely, fabricating a solid metal nose cap from the aluminum sheet. They mounted 4 M2 Browning guns in the nose, arranged in a rectangular pattern, all pointed forward and bore-sighted, to converge at 300 yards. They fabricated ammunition boxes that fit in the available space, feeding belts to the guns. The initial test installation added approximately 600 pounds to the aircraft's nose, 4 guns at 64 pounds each, plus mounting hardware, plus 1,500 rounds of ammunition at approximately 100 rounds per gun. The first test flight nearly ended in disaster. The pilot, whose name is lost to history, but whose experience was recorded in maintenance logs, reported that the aircraft wanted to nose down during takeoff. The forward center of gravity made the bomber nose heavy, requiring constant back pressure on the control yoke. During flight, handling characteristics changed. The aircraft felt sluggish in pitch, and when the pilot test-fired the guns at altitude, the recoil was violent enough to slow the aircraft noticeably and create a pronounced nose-down pitch moment. Gunn returned to the drawing board. He repositioned the guns slightly aft within the nose section, improving the center of gravity. He reduced the ammunition load from 1,500 to 1,200 rounds, saving weight. He consulted with other pilots and mechanics, refining the installation. By February 1943, the modifications were proven enough for combat testing. General George Kenney, commanding the 5th Air Force in the Southwest Pacific, approved limited deployment of modified aircraft. The first combat test came during the Battle of the Bismarck Sea, the convoy operation that opened this narrative. Intelligence had identified a major Japanese convoy departing Rabaul on February 28, 1943, bound for Lae in New Guinea. The convoy carried the 51st Division's main strength, approximately 6,900 soldiers plus equipment and supplies. Losing this convoy would cripple Japanese defensive capabilities in New Guinea. Allied air forces prepared a maximum effort. The plan involved multiple attack waves over several days, combining high-altitude bombing by B-17 flying fortresses, medium-altitude attack by conventional B-25 seconds, and low-altitude masthead bombing by modified Strafer B-25 seconds using a new tactic Gunn had developed: skip bombing. Skip bombing was conceptually simple but technically demanding. Aircraft approached the target at extremely low altitude, 50 to 100 feet above the water at high speed. At ranges between 250 to 400 yards from the target ship, the pilot released bombs with a delayed fuse. The bombs, traveling at the aircraft's forward speed, skipped across the water surface like a stone, struck the ship's hull at or below the waterline where armor was thinnest, and detonated seconds later inside the hull. The tactic was devastatingly effective against ships, but required pilots to fly straight and level at point-blank range, while ship-based anti-aircraft guns fired directly at them. This was where the Strafer's heavy forward armament proved its value. The modified B-25 seconds approached their targets with all 4 nose guns firing, suppressing anti-aircraft positions before the ship's gunners could bring effective fire to bear. 4 50-caliber guns, firing in unison at 800 rounds per minute each, created a cone of fire containing over 50 bullets per second. Tracers every 5th round, loaded with a pyrotechnic compound that burned brightly, created visible streams of fire that had a profound psychological impact on enemy gunners. Men manning anti-aircraft positions, seeing a solid wall of tracers approaching, often abandoned their guns or fired wildly without aiming. Those who remained at their posts were frequently killed before they could effectively engage the attacking bomber. The attack on March 3rd was methodical and brutal. B-17 seconds attacked first from high altitude, achieving few hits but forcing the convoy to scatter defensive formation. Then the B-25 seconds came in at low level. 8 modified strafers led the attack, approaching at wave-top height at speeds approaching 250 miles per hour. The lead bomber, piloted by Captain Larner, the same officer who'd written pessimistically about bomber vulnerability 2 months earlier, selected a transport ship as his target. At 1,000 yards, he opened fire with all 4 nose guns. The tracer streams walked across the water, then reached the ship's superstructure. Gun positions along the deck went silent. At 300 yards, Larner released his bombs, pulled up sharply, and watched as 2 500-pound bombs skipped across the water, struck the transport's hull, and detonated below the waterline. The ship began listing immediately. 7 more strafers followed in quick succession, each selecting a target, each suppressing defensive fire with overwhelming forward firepower, each delivering skip-bombing attacks at point-blank range. The conventional B-25 seconds, carrying standard bomb loads, attacked from slightly higher altitude. Japanese fighter cover, expected to be the primary threat, proved less dangerous than anticipated. The Zeros that attempted to intercept the strafers discovered what Okumura had learned. Approaching a B-25 from the front was no longer a safe option. The strafers didn't defend, they attacked. Pilots fired their nose guns at intercepting fighters, forcing the Zeros to break off or risk flying into concentrated 50 caliber fire. Over 3 days of continuous attack, Allied aircraft sank all 8 transports and 4 of 8 destroyers. Of the 6,900 Japanese soldiers aboard the transports, fewer than 1,000 reached shore. The rest drowned or were killed during the attacks. The Battle of the Bismarck Sea was the most decisive Allied air victory in the Southwest Pacific to that date, and the modified B-25 strafers had proven their concept in the most demanding combat conditions imaginable. Japanese military intelligence immediately recognized they'd encountered something new. Interrogation reports from captured aircrew who survived attacks on subsequent convoys contain references to American bombers with cannon-like forward armament and impossible concentration of fire from the nose. Some reports describe the B-25 strafers as flying battleships, a term that would become common in Japanese tactical assessments. The psychological impact was significant. Japanese fighter pilots, trained to exploit bomber vulnerabilities through frontal attacks, suddenly faced bombers that shot back with firepower exceeding many fighters. The tactical equation had reversed. Bombers were no longer prey. Word of the strafers' success spread rapidly through the 5th Air Force. Pilots who'd been flying conventional B-25 seconds requested transfers to starter squadrons. Ground crews, seeing the combat footage and hearing pilot accounts, began volunteering for modification duties. General Kenny, impressed by results, ordered an expanded modification program. By May 1943, 5th Air Force maintenance depots were converting dozens of B-25 seconds to starter configuration. But Gunn wasn't satisfied with 4 guns. If 4 guns worked, more would work better. The evolution from 4 guns to what eventually became the most heavily armed production aircraft in the American inventory happened through rapid iteration driven by combat feedback. By mid-1943, Gunn and his teams were installing 650 caliber guns in B-25 C and D models, 4 in the nose, 2 in cheek blisters on either side of the forward fuselage, then 8 guns, then 10. Each modification required solving new engineering challenges. Weight distribution remained critical. Ammunition storage became increasingly complex. Recoil forces multiplied. The airframe itself had limits. There was only so much weight and structural stress the B-25's design could accommodate before flight characteristics degraded unacceptably. The standardization of these field modifications came with the B-25G model, which entered production in October 1943. North American Aviation, the B-25's manufacturer, incorporated the strafer concept into a production variant. The G model mounted a 75mm M4 cannon in the nose, the same gun mounted on M3 Grant and early M4 Sherman tanks, along with 250 caliber machine guns. The concept was to provide bomber crews with anti-shipping capability against armored targets. The 75mm cannon could penetrate light naval armor and could destroy coastal fortifications or hardened ground targets. It fired a 14-pound projectile at 1,800 feet per second muzzle velocity, with an effective range of approximately 1,000 yards. Testing the 75mm installation revealed significant challenges. The gun's recoil, substantially greater than machine gun recoil, required heavy reinforcement of the nose structure. The entire aircraft shuddered when the cannon fired. Accuracy was problematic because the gun was rigidly mounted. Aiming required pointing the entire aircraft at the target. The rate of fire was slow, approximately 4 rounds per minute maximum, limited by the need for manual loading, and ammunition capacity was severely restricted. The B-25G could carry only 21 rounds of 75mm ammunition. Crews had to make every shot count. Despite these limitations, the 75mm installation proved effective in specific tactical situations. Against large ships, concrete bunkers, or armored trains, the cannon provided firepower that machine guns couldn't match. Gun camera footage from B-25G operations in the Pacific shows the 75mm round's impact against Japanese cargo vessels. The shell would strike the hull, penetrate, and detonate inside, often causing catastrophic secondary explosions if the round hit ammunition or fuel storage. But the cannon was situational. For most targets, machine guns were more practical, higher rate of fire, greater ammunition capacity, and sufficient destructive effect against the majority of target strafers engaged. North American Aviation's next production variant, the B-25H, represented the culmination of the strafer concept. It entered production in July 1944 and mounted the 75mm cannon, plus 1450 caliber machine guns, 4 in the nose, 4 in cheek blisters, 2 in the tail turret, 2 in waist positions, and 2 in a dorsal turret. Fully armed and loaded, a B-25H carried over half a ton of ammunition. The forward armament alone, the cannon plus 8 forward-firing 50 calibers, delivered more firepower than many destroyers' secondary batteries. This was no longer a medium bomber. It was a flying weapons platform, designed specifically for ground attack and anti-shipping missions. The psychological impact of encountering a B-25H in combat defied traditional military assessment metrics. Wehrmacht after-action reports from Italy in late 1944 contain accounts that read like exaggerations but are corroborated across multiple independent sources. A report from Panzer Grenadier Regiment 129, operating near Anzio in January 1945, describes an attack by American twin-engine bombers employing direct-fire artillery and simultaneous machine gun bombardment. The report notes that the attack destroyed 3 armored vehicles, killed 14 soldiers, and forced the battalion to abandon a planned counterattack because forward positions came under sustained fire from aircraft-mounted artillery beyond the effective range of anti-aircraft weapons. To understand the shock this caused German forces, context is essential. German soldiers in Italy were veterans. Many had fought on the Eastern Front. They'd experienced Soviet ground attack aircraft, particularly the Ilyushin Il-2 Sturmovik, which mounted cannons and rockets. But the Sturmovik was a single-engine, relatively slow aircraft that attacked individually or in small groups. The B-25H attacked in squadron strength 12 to 18 aircraft at once each, mounting firepower equivalent to a light tank, all arriving simultaneously at a single target area. The volume of fire was unprecedented. Staff Sergeant Heinrich Böll, writing in his diary in March 1945 while serving with the Wehrmacht's 26th Panzer Division in northern Italy, recorded his experience of a B-25H attack. The sound comes first engines, many engines, low altitude. Then we see them, perhaps 12 aircraft in loose formation. We take cover. Anti-aircraft guns open fire, but the aircraft do not deviate. They come straight toward our position. Then the firing begins. I cannot adequately describe it. Not machine guns in the sense we understand. This is a continuous roar, like fabric tearing but magnified beyond reason. The ground erupts. Trees shatter. One bomber fires what appears to be a cannon, an actual cannon from its nose. The round strikes an SD, KFZ, 251 half-track, 30 meters from my position. The vehicle explodes. The entire attack lasts, perhaps 90 seconds. When it ended, our battalion had lost 9 vehicles and 23 men. We did not inflict any damage on the attackers. Boll survived the war and became a noted German author. His wartime diaries were published in 1972, and this account can be verified against his unit's casualty records. While strafer operations expanded in the Pacific and Mediterranean theaters, the concept spread to other air forces and commands. In North Africa, the 12th Air Force began receiving modified B-25 seconds in mid-1943. The desert environment presented different tactical challenges than the Pacific. Targets were more often ground-based airfields, supply depots, vehicle columns, fortified positions. The open terrain meant anti-aircraft defences could be extensive and well-positioned. German flak units in North Africa were experienced and disciplined, having fought the RAF for 2 years before American forces arrived in theatre. The 97th Bombardment Group, operating from Tunisia in summer 1943, converted its B-25 infantry to strafer configuration and developed tactics specifically for desert operations. Instead of the ultra-low altitude approach used for anti-shipping work, the 97th's crews approached targets at 500 to 1,000 feet, fast and from unexpected directions. They'd identify targets using intelligence reports, German fuel dumps, ammunition storage, airfield facilities, then plan approach routes that minimized exposure to known flak positions. The strafers would come in fast, possibly 260 to 280 miles per hour at low level, firing their nose guns throughout the attack run to suppress ground fire, then exit the target area using terrain masking when possible. Captain Robert Wilkins, flying with the 310th Bombardment Squadron of the 97th Group, described a typical mission in his post-war memoir, published in 1958. We hit a German supply depot near Bizerte in August 43. Intelligence said it contained fuel and ammunition for Rommel's retreating forces. We came in from the north at dawn, sun behind us, 8 aircraft in loose formation. At 2 miles out, I could see the target rows of fuel drums, stacked ammunition crates, several trucks. Flak started immediately, black puffs tracking across the sky, but we were moving fast and jinked slightly to throw off their aim. At half a mile I opened up with all nose guns. The tracers walked across the depot. Fuel drums erupted in flames. Secondary explosions began before we reached the drop point. I released 6 250-pound fragmentation bombs, pulled up sharply right to avoid the explosions, and we were clear. The entire attack, from first tracer to wheels up from the target, maybe 30 seconds. Behind us, the depot was a firestorm. The 97th's tactics became doctrine for 12th Air Force strafer operations. Speed and surprise trumped heavy fighter escort. Small formations attacked multiple targets simultaneously, overwhelming German defensive responses. And the heavy forward armament meant single strafers could suppress ground fire long enough to complete their bomb runs. Loss rates, while never negligible, were substantially lower than conventional medium bomber operations at similar altitudes. The 97th flew 174 combat missions between July 1943 and May 1944, losing 18 aircraft, a loss rate of approximately 10%, high by later war standards but remarkably low given the low-altitude attack profile and heavily defended targets. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. As 1944 progressed and Allied forces advanced into France and Germany, B-25 Strafer squadrons operating from English and French bases found new roles. The 9th Air Force's bombardment groups supported ground forces during the Normandy invasion and subsequent campaign across France. Strafers attacked bridges, rail junctions, German strong points, and vehicle columns. The tactical situation in France differed significantly from North Africa or the Pacific. Germany's Luftwaffe fighter forces, though depleted by attrition over 2 years of combat, remained dangerous. German flak defences were the most sophisticated in the world, employing radar-directed guns and experienced crews, and the close proximity of friendly ground forces meant accurate target identification was critical. Fratricide risk was ever present. The 416th Bombardment Group, flying from bases in France from August 1944 onward, specialized in tactical support for ground forces. Their mission reports, preserved in National Archives records, detail the complexity of close air support in the European theatre. A typical mission might involve a request from ground commanders for strikes against a German position holding up an advance. The 416th would dispatch a flight of 4 to 6 strafers, coordinated with a forward air controller who could see both friendly positions and the target. The strafers would arrive on station, contact the controller, receive target identification, often using smoke markers or distinctive terrain features, and then attack with extreme precision to avoid hitting friendly forces, sometimes only a few hundred yards from the target. First Lieutenant James Keefe, pilot with the 416th, flew 63 combat missions between September 1944 and April 1945. His account, recorded in an oral history interview conducted in 1991, describes the tension of close support missions. You're coming in at 300 feet, doing 250 knots, and you have maybe 5 seconds to positively identify your target before you commit to the attack. Friendly troops are close enough that if you're off by even 100 yards, you're killing Americans or Brits. The pressure is immense. But the strafers' firepower made us effective. We could put 850 calibers on target with pinpoint accuracy. I've seen us take out a single building in a French village where Germans were holed up, saturate it with fire, and leave the buildings on either side untouched. That kind of precision saved lives our guys on the ground. The final production variant, the B-25J, entered service in December 1943, but continued production through the war's end. It wasn't specifically designed as a strafer, but many J models were field-modified to carry 1250 caliber guns, 8 in the nose and forward fuselage, 2 in the dorsal turret, 2 in the tail. The J model represented standardization of lessons learned through 2 years of combat. It was faster than earlier models, better armored, and its airframe incorporated structural reinforcements that allowed heavy armament without the handling issues that plagued early conversions. By 1945, B-25 strafers operated in every theater where American forces fought. In the Philippines, they supported MacArthur's return campaign, attacking Japanese positions throughout the archipelago. In Burma, they flew missions along the Ledo Road and against Japanese supply lines. In China, they supported Chinese nationalist forces fighting Japanese occupation armies. In Italy, they intercepted German supply routes through the Alps. In France and Germany, they ranged ahead of advancing Allied armies, destroying anything that could support German resistance. The strafer had become ubiquitous, a standard weapon in the American tactical air arsenal. But the human cost remained severe, despite the aircraft's effectiveness. Flying at low altitude against defended targets meant exposure to every weapon the enemy possessed. Anti-aircraft artillery, particularly German 88mm flak guns, remained deadly throughout the war. Small arms fire could damage or destroy a low-flying aircraft. A lucky rifle shot could kill a pilot or sever a control cable. And while the strafer's heavy armament deterred fighter attacks, determined or desperate enemy pilots still pressed home attacks. Between 1943 and 1945, American forces lost approximately 400 B-25 seconds in combat across all theaters. Each aircraft represented 6 crew members. Approximately 2,400 men killed, wounded, or captured. The strafer's firepower made it effective. It didn't make it safe. The psychological dimension of the strafer's impact deserves careful examination because it represents a reversal that military theorists hadn't predicted. Bombers were supposed to be vulnerable. This was axiomatic in air combat doctrine developed during the interwar period and the war's early years. Fighters attacked bombers. Bombers defended themselves and relied on fighter escorts for protection. The relationship was predator and prey, with roles clearly defined. The B-25 strafer disrupted this relationship fundamentally. It created a situation where bomber pilots actively engaged enemy fighters, where medium bombers hunted fighter aircraft, where the prey became predator. Luftwaffe combat reports from 1944 and 1945 show the doctrinal confusion this caused. German fighter pilots, particularly less experienced pilots replacing combat losses, encountered B-25 strafer formations and attempted standard frontal attacks, only to find themselves facing firepower that exceeded their own aircraft's armament. The psychological impact was profound. A fighter pilot expected advantages in speed, maneuverability, and armament. Against a strafer, 2 of those 3 advantages disappeared. The B-25 wasn't faster, but it didn't need to be. It wasn't. More maneuverable, but again, unnecessary. Its armament advantage was so overwhelming that many fighter pilots broke off attacks before reaching effective firing range. Oberleutnant Franz Stigler, a Luftwaffe fighter ace who survived the war and whose combat reports are preserved in German military archives, described an encounter with B-25 strafers over Italy in February 1945. I led my Schwarm 4 Bf-109G aircraft to intercept a reported formation of American bombers near Bologna. We identified 6 B-25 seconds at low altitude, apparently returning from a ground attack mission. I positioned myself for a standard frontal approach, intending to engage the lead bomber and break away. At 800 meters, the bomber opened fire. All my experience suggested this was premature. Bombers typically held fire until much closer range, but the volume of fire was extraordinary. Tracers filled the air between us. My number 2, Feldwebel Hartmann, took hits immediately. His engine began smoking. I broke left, abandoning the attack. We couldn't close to effective range against that firepower. Hartmann crashed 5 kilometers from the engagement site. He survived but was badly burned. Stigler's account is particularly valuable because he was an experienced pilot with over 400 combat missions. He wasn't a novice misidentifying the threat. His assessment was tactical and objective. Engaging B-25 strafers from the front was unacceptably dangerous. This assessment spread through Luftwaffe fighter units as experienced pilots shared their experiences. By late 1944, Luftwaffe tactical manuals had been updated to recommend against frontal attacks on heavily armed American medium bombers, a designation that referred specifically to strafer variants. The Japanese experience paralleled Germany's. IJN and IJA fighter units operating in the Southwest Pacific and Philippines encountered B-25 strafers throughout 1943 and 1944. Japanese tactical doctrine, like German doctrine, emphasized frontal attacks against bombers. The Zero fighter, Japan's primary naval fighter, was lightly built and fast, but carried relatively light armament, two 20mm cannons and two 77mm machine guns in most variants. Against a strafer's 8 or more 50 caliber guns, the Zero was outgunned and vulnerable. Japanese combat reports from this period describe American bombers as heavily armed or fighter-like in defensive capability. What made this psychological impact particularly significant was its cumulative effect. Early in the war, bomber crews were defensive. They flew formation, maintained discipline, and relied on mutual defensive fire. Fighter pilots could approach with reasonable confidence, accepting calculated risks. The strafer reversed the psychological equation. Fighter pilots approaching strafer formations faced not calculated risk but near certainty of encountering overwhelming fire. This created hesitation, caution, and in some documented cases, outright refusal to engage. German and Japanese fighter pilots were brave, this isn't questioned. But bravery has limits when tactical situations make success improbable and casualties near certain. Mission reports from German fighter units in Italy and France during late 1944 show increasing instances of fighters breaking off engagements with strafer formations before reaching effective firing range. Some reports cite mechanical issues or fuel concerns, but the pattern suggests reluctance to press attacks against overwhelming firepower. This wasn't cowardice, it was a rational tactical assessment. A fighter pilot's duty was to intercept and destroy enemy aircraft. But if pressing the attack meant near certain loss of your own aircraft for uncertain probability of destroying the target, the tactical calculus didn't support engagement. Better to disengage, preserve your aircraft, and engage a different target under more favorable conditions. The strategic implications of this psychological shift were significant. If enemy fighters wouldn't engage straighter formations, those formations could operate with impunity at low altitude. This freed fighter escorts for other duties. It allowed strafer squadrons to range deep into enemy territory without heavy protection, and it meant ground targets had fewer defenses available if fighters wouldn't engage the strafers. Those targets depended entirely on anti-aircraft fire for protection. The B-25 strafer, through overwhelming firepower and psychological dominance, had carved out a tactical niche where it operated as a predator with few natural threats. The technical evolution of the strafer concept influenced post-war aircraft design in ways that remain visible in modern military aviation. The fundamental innovation mounting fixed, forward-firing guns in numbers that transformed the aircraft's role became doctrine for specialized attack aircraft. The Douglas A-26 Invader, which entered service in 1944, incorporated Strada principles from the design stage rather than as a field modification. It mounted 6 to 8 50 caliber guns in the nose and wings, plus gun pods carrying additional weapons. The A-26 served through Korea and Vietnam, remaining in active service for nearly 30 years. But the most direct lineage runs from Pappy Gunn's modified B-25 seconds to the AC-130 gunship and its successors. The AC-130, first deployed in Vietnam in the late 1960s, took the strafer concept to its logical extreme. Mount overwhelming firepower on a stable platform, orbit the target, and deliver sustained fire with precision. Modern AC-130 variants mount 20mm Gatling guns, 40mm cannons, and 105mm howitzers. The tactical doctrine sustained fire support, suppression of ground defenses, precision engagement traces. Directly to principles Gunn and his mechanics developed in dusty Pacific workshops during 1943. Paul Gunn continued flying combat missions throughout the war. His personnel file records over 200 combat sorties in multiple aircraft types. He survived the war without serious injury, remarkable, given his aggressive flying style and constant exposure to combat. On February 3, 1945, American forces liberated Santo Tomas internment camp in Manila. Gunn's wife and children, alive but weakened by 3 years of captivity, were freed. Gunn learned his family was safe on February 5th, when a telegram reached 5th Air Force headquarters. He'd spent 3 years fighting, inventing, and risking his life, driven by rage and hope in roughly equal measure. The hope was validated. His family survived. He remained in the Philippines after the war, working briefly for the new Philippine government before returning to the United States. The Army Air Forces awarded him the Distinguished Service Cross, the Silver Star, the Distinguished Flying Cross, and numerous other decorations. In citations, his superiors credited him with developing tactical innovations that saved countless American lives. General George Kenney, in his post-war memoir published in 1949, devoted an entire chapter to Gunn's modifications and their impact on 5th Air Force operations. Kenney wrote, "Pappy Gunn's strafer modifications gave us offensive capability we desperately needed. His work transformed the B-25 from a vulnerable medium bomber into the most effective ground attack aircraft in the Pacific theater. I believe his innovations shortened the war in the Southwest Pacific by months." Gunn died in 1957, at age 57, from a heart attack. He was buried with military honors. News of his death received minimal press coverage. He wasn't famous. He'd never sought publicity. His innovations were credited to field modifications, or 5th Air Force engineering in most official histories. For decades, his name appeared primarily in specialist military aviation literature. Only in recent years, as historians examined maintenance records and personal accounts from Pacific Theater veterans, has Gunn's central role in developing the strafer become widely recognized. The B-25 strafer itself passed into history with surprising speed after the war. The aircraft that had dominated low-altitude combat from 1943 through 1945 was declared obsolete by 1948. Jets were the future. The B-25, with its reciprocating engines and World War II-era design, represented the past. Thousands were scrapped or sold as surplus. A few remained in service with Allied air forces through the 1950s. Some were converted for civilian use cargo haulers, executive transports, fire bombers, but the strafer variants, heavily modified and specialized, were mostly scrapped. Their armor was being removed, their excess guns stripped, their unique capabilities lost as the aircraft themselves disappeared. Yet the principles endured. The idea that overwhelming firepower could transform an aircraft's tactical role. the concept of mounting more guns than seemed reasonable or necessary, the willingness to question doctrine and modify equipment based on combat feedback rather than peacetime theory. These principles shaped post-war close air support doctrine. They influenced attack helicopter design in the 1960s and 70s. They informed the development of the A-10 Thunderbolt II, with its massive GAU-8 Avenger cannon, in the 1970s. The Strafer's legacy isn't the aircraft itself, but the tactical philosophy it represented. Adapt weapons to missions rather than forcing missions to fit available weapons. Looking back from our present perspective, 80 years after these events, the B-25 Strafer story reveals something fundamental about innovation during wartime. The innovation wasn't technological. The .50 caliber machine gun existed before guns started his modifications. The B-25 airframe existed. The tactical problem bomber vulnerability to frontal attacks was widely recognized. What gun provided wasn't new technology but new thinking. He questioned the assumption that bombers had to be vulnerable. He recognized that the same industrial capacity producing thousands of machine guns could provide overwhelming firepower if those guns were properly concentrated. And he had the practical mechanical skill to implement his ideas despite institutional resistance. This pattern repeated throughout World War II. The Manhattan Project didn't invent nuclear physics. It applied existing knowledge to create a weapon. Radar wasn't discovered during the war. It was refined and deployed widely. The proximity fuse, the bazooka, the Higgins boat, the Liberty ship, innovation after innovation came from applying existing technology in new ways or scaling production of proven designs. World War II wasn't won by science fiction weapons that didn't exist in 1939. It was won by taking what existed and using it better, faster, and in greater quantities than the enemy. The B-25 Strafer embodied this principle. It was a standard medium bomber, mass-produced by the thousands, modified with standard machine guns already in the supply system. The modification could be performed by competent mechanics in field workshops without specialized tools. The ammunition was standard .50 caliber, available from existing production. There was nothing exotic about the Strafer. What was extraordinary was the willingness to modify a bomber to perform like a fighter, to question the doctrinal assumption that bombers were inherently vulnerable to frontal attack, and to recognize that sometimes the solution to a tactical problem isn't a new weapon but a new way of using existing weapons. The Germans and Japanese could have developed similar modifications. They had capable bombers, effective guns, and talented engineers. They didn't, partly because their military cultures were less amenable to field modifications that challenged official doctrine, but also because they were fighting defensive campaigns where innovation was harder to implement and test. Innovation requires resources, time, and willingness to accept risk. By 1943, when the Strafer was developed, America had all three. Germany and Japan had none. They were fighting for survival, conserving resources, and couldn't afford expensive experiments that might fail. This asymmetry, American ability to innovate versus Axis inability to respond, compounded throughout the war. The Strafer was one example among hundreds. American forces could test modifications, adopt successful ones, standardize them in production, and deploy them in overwhelming numbers. German and Japanese forces could recognize the threat, write defensive, tactical, doctrine, and watch as their disadvantage grew wider. By 1945, this gap was unbridgeable. Germany and Japan faced enemies who could field weapons they couldn't counter, and who could innovate faster than they could respond. The morning of March 3rd, 1943, when squadron leader Okumura watched his wingman Zero disintegrate and barely escaped the same fate, represented a turning point. Not a strategic turning point, the war's outcome was already determined by industrial capacity and resource availability, but a tactical turning point, the moment when bomber crews stopped being inherently vulnerable prey and became hunters, the moment when fighter pilots had to calculate whether engaging bombers was worth the risk, the moment when Paul Gunn's anger and mechanical skill changed air combat doctrine in ways that rippled through decades of subsequent military aviation. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.